Okay, so I'm going to redo the lecture because I forgot to record it during regular class time. Okay, so remember we're talking about similarity. Similarity is the topic here. Okay, and before we get started, let me introduce some notation. Something that we've used a lot of times, but I want to give it a name now. So if we have a vector space V, and we have B a basis, so B being vectors B1 through Bn, a basis of V, then, as you know, there's going to be this map from V to R sub n, Rn, right? Euclidean space, n-dimensional Euclidean space. The one that takes the vector, and then takes the vector, and then maps it to the coordinate vector with respect to that basis. Okay, let's call that thing pi sub b. Okay, pi sub b. So pi sub b is going to be the thing that, right? Pi sub b is going to be the map from V to Rn that takes a vector which has some expression as a linear combination of the bi's, and then maps it to the Euclidean vector of those coefficients used in the linear combination. Okay, so this is the coordinate vector map. Coordinate vector map, right? And remember that this map is 1-to-1 and onto, right? In other words, it's an isomorphism. Right? And because it's an isomorphism, so there exists a inverse map that's also a linear transformation. So there's a linear transformation, the map that goes in reverse, right? The one that goes from the coordinates back to the vector, right? So you can start with a bunch of coordinates down here and then map them back upwards to the vector that corresponds to those coefficients, that has those coefficients. Okay, so yeah. Right, and remember we're talking about matrix representations of a linear transformation, right? You've got some map going from one vector space to another vector space. You've got a basis over here and the corresponding coordinate vector map into Rm, right? And what we've been talking about are the matrix representations, right? The matrix, the n by n matrix that gives you a map from Rn to Rm that makes the diagram commute, right? That makes it that you can go this way or you can go that way, right? That if you take t and then follow it with pi sub v, if you take t and then follow it by pi sub b, it's the same thing as if you took pi sub b and then followed that with t sub a. Right? Right. In other words, t sub v's coordinate vector with respect to the v basis is the same thing as a applied to the coordinate vector with respect to b of v. Right. That's what it means to be a matrix representation. Okay. Okay. And let me also note that because right. So right now we have a A is the matrix representation is the same thing as saying that for all v, you know, t of v hit with changed into the coordinate vector with respect to v is the same thing as v's coordinate vector with respect to b hit with the matrix, right? Right, but because these maps are isomorphisms, we can actually go from here up to here and then across and then down, and that would be the same thing as this. In other words, if I took a vector and then mapped it backwards through the coordinate map, and then hit that with t, and then mapped it forwards through the other side's coordinate map. Well, that would be the same thing as hitting the vector with A. Okay, so yeah, so actually in this picture, you know, going across and down is the same thing as going down and across, but also going across is the same thing as going up, across, and down, or going across up here is the same as going down, across, and then back up. Okay, so in case, yeah, okay. Okay, okay, so we actually started class with an exercise, which was, suppose you have a linear transformation from v to v. Then show that any matrix representation of T is non-invertible. Okay, so if you have some basis B and some other basis B prime that give you maps, give you isomorphisms down to Rn on either side, and you have some matrix representation, then the matrix, the matrix that represents that linear transformation can't be invertible. Okay, and people were able to do this in class. So somebody said, well, look, I'm sorry. Show that. Sorry. Assume that the kernel of T is not just the zero vector. The kernel of T has some non-zero vectors in it. In that case, show that the matrix representation is non-invertible. Sorry, I got something in my eye. Okay, so one of you was able to figure it out. You said, well, look, choose somebody in the kernel. So let's say that this V0 is in the kernel. In that case, when you map it through T, you're going to get 0, right? So T of V0 is the zero vector over here in V, right? And then when you map that down here, well, this is going to be 0, right? It's going to be the zero vector, 0, 0, 0, 0, 0, right? Right? Because this is 0, and then it gets mapped through this linear transformation, so it gets sent to 0. Okay. Now, if you bring it down this way, you get. So this guy is non-zero, right? You bring it down, you take its coordinate vector. Well, its coordinate vector is going to be non-zero, right? Because this pi sub b is an isomorphism, so it can't take two different things to 0. So it can't take this thing to 0 because it already takes 0 to 0, right? So you get something down here, the coordinate vector of v naught with respect to b, but that's not 0, right? That's not the 0 vector. And then you hit it with a, right? Well, when you hit it with a, you should get this thing over here, right? So a of this non-zero thing, equals this, which is 0, right? So that means that, what does that mean? That means that ax equals 0 has non-trivial solutions, right? Has non-trivial solutions, right? And so that means that A is non-invertible. So A non-invertible, right? Okay, let me write that properly because I've just drawn a picture here. Okay, so proof. Let A be the matrix representation of T with respect to bases B and B prime. Since the kernel of T is non-zero, so choose some V naught that's not equal to 0, such that T of V naught is 0. But then, the coordinate vector of V naught with respect to B is non-zero, but A of V naught with respect to B is T of V naught with respect to B prime, because A is a matrix representation, right? But T of V naught is 0, so 0's coordinate vector with respect to B prime is going to be 0. It's going to be all zeros, right? So, so we have a non-zero vector that gets mapped to 0 by A, right? In other words, A has a non-trivial null space, so A cannot be invertible, right? So A is not invertible. That's the end. Okay, so that was the warm-up. That was the warm-up question. And now let's talk about similarity. I guess I can erase this because this is a video. Okay, so similarity. So here's the idea. So we're going to be dealing with what the book calls linear operators. That is, linear transformations from one vector space to itself. Okay, and we'll be considering matrix representations, but with respect to the same basis on both sides. So we just take a single basis, right? So let B be a basis of V, right? And then we'll take the coordinate vector map with respect to B. We'll take the coordinate vector map with respect to B on that side also, right? And then we'll have a matrix representation which we'll call A sub B, B, say. Sometimes I'll make it sloppy and just call it A sub B because I know that the second B is the same as the first B. But in any case, the coordinate, the matrix representation with respect to the B basis and the B basis, that makes this, the one that makes this diagram commute. Okay, so, right, if you have a linear operator and you have a basis, then you can have this matrix representation with respect to the same basis on both sides, Okay, so that gives you one matrix representation, right? But suppose you have another matrix representation, right? Suppose you have another basis. Let's say that B and B prime are both bases. Bases of B, right? Well, in that case, you're gonna have a projection. You're gonna have this coordinate vector map, pi sub B prime, that takes the vectors to their coordinate representations, coordinate vectors with respect to the B prime basis, right? And in that case, you're going to get a different basis, AB prime, B prime. You're going to get a different matrix representation, AB prime, B prime, right? So the question is, what's the relation between AB prime, AB, B, and AB prime, B prime? And now I see why I just wrote it one time. A sub B and A sub B prime. Okay. Okay. And the answer is, here's the theorem, that if we let S sub B prime, S sub B prime be the transition matrix from B to B prime. In other words, the one that takes the map taking the coordinate vector with respect to B to the coordinate vector with respect to B prime. Okay. Then ABB is the same thing as B prime. I want to do that first. Yeah, is the same thing as SBB prime followed by ABB followed by SBB prime inverse. Okay, and remember that SBB prime inverse actually is the same thing as SB prime B. Okay, so it turns out that if you have one matrix representation of a linear operator, and you have another matrix representation of the same linear operator, then they're somehow related. This process of taking a matrix and then multiplying it on the left by the inverse and multiplying it on the right by this invertible matrix is called conjugation. Okay, and so what you say is that this matrix is a conjugate of that matrix. Okay, so notice that if this guy is a conjugate of that guy is certainly a conjugate of this guy, because you can just pull the inverse of the matrix over onto the left. Okay, so what it's saying is that every linear operator is associated with it's associated with a bunch of different matrices, but those matrices are actually somehow just the same matrix in disguise. They're just like disguised versions of the same matrix. Okay, there's really only, in some sense, there's really only one matrix that's, in some sense there's only one matrix, but it's really all the conjugates of that one matrix. Okay. Let me remind, in case people have forgotten, let me put up this reminder that if you have given a vector space V with bases B and B prime, being so B1 to Bn, and B1 prime to Bn prime, then the transition matrix from B to B prime, from B to B prime, is obtained by expressing from B to B prime is obtained by expressing the elements of B in terms of B prime, right? So you remember, we would say, well, B1 equals, S11 B1 prime plus S21 B2 prime plus Sn1 Bn prime. B2, you express B2 in terms of the B primes, Bi primes, all the way down to Bn, S1n B1 prime plus Snn Bn prime, and then you take you take the transpose of these coefficients, right? You express the B basis in terms of the B prime basis, and then the transition matrix is going to be, sorry, this is bad board work, but I'm going to do it. B prime is going to be S11 Sn1 S1n Sn1. Right. That was the transition matrix, in case if you don't remember. Okay. So okay. So this is the theorem. This is the theorem saying saying that the matrix representations are related to each other. Matrix representations are related to each other. Okay, so let me give an example. Let me give an example just to make that concrete. Okay, and then we'll explain why it's true. Okay. Oh, actually, before we do that, let me comment that. So remember what that matrix does. That's the matrix that takes, right? SB B prime is going to be the matrix that takes the representation with respect to the B basis, and then gives you back the coordinate vector with respect to the B basis, and then gives you back the coordinate vector with respect to the B prime basis, right? So in the picture here, it goes from down here up to here, right? Right. Remember, this guy takes this to its coordinate vector with respect to B. This guy takes V to its coordinate vector with respect to B prime, right? And so what SB prime does is takes the coordinate vector with respect to B and then takes it to the coordinate vector with respect to B prime, right? So in a very, you can see, I hope, that this thing is actually the composition of the inverse of this guy with this guy, right? You take a vector down here, run it backwards through this isomorphism, and then run it forwards through this isomorphism. That goes from the coordinate vector with respect to B to the coordinate vector with respect to B prime. Well, that's exactly what S does. Okay, so S is just this map in reverse followed by this map, right? Where this by composition I mean just like in pre-calculus, f composed with g means f of g of x. Right? You do this thing first, and then you take the output and then run it into this thing. Okay, so let's do the example. The example is, again, differentiation. On P3. Okay, so we have polynomials of degree less than 3. Excuse me. So let me write it down here. Polynomials of degree less than 3. We have one basis. We have one basis, b, which is the standard basis. So b is 1x squared. That gives us coordinate maps like here, and then we get a matrix representation, right? The matrix representation, we saw this before, 0, 0, 0, 1, 0, 0, 0, 2, 0. Right? Remember how you get it. You take t and you apply it to each of these guys. You take the transformation, which we call d, sorry. Take d and then apply it to each of these guys, and then represent them in terms of this basis on the other side. Right? And those are going to be the columns of your matrix. Right? So 1 goes to 0, which with respect to this basis has a coordinate vector 0, 0, 0. X goes to 1, which in this coordinate vector, its coordinate vector will be 1, 0, 0. Right? And this guy goes to 2x, which is going to be 0 of this guy, 2 of this guy, and 0 of this guy, and 0, 2, 0 here. Okay. Okay. We have another basis, let's call it b prime, which is 1, 2x, 4x squared minus 2. Right? And again, that guy gives us a different coordinate, a different matrix representation. I should call this a sub b, and call this guy a sub b prime. Right? And we want to see that a sub b and a sub b prime are related in the way that we said earlier. Sorry, I erased it already. Okay. Okay. So, let's see. Yeah, actually, let's just calculate what a sub b prime will be, right? Calculating what a sub b prime will be, well, b of 1 is 0, expressed with respect to the b prime basis, that's going to be 0, 0, 0. Right? D of 2x is 2 with respect to that basis. With respect to the b prime basis, it's going to be 2, 0, 0. Right? And d of 4x squared minus 2, 4x squared minus 2 is 8x. 8x is 0, 4, 0, right? So 0, 4, 0. Right? And you get that a sub b prime is the matrix 0, 0, 0, 2, 0, 0, 0, 4, 0. Okay. And now we want to see that that these two representations are in fact related by the transition matrix from B to B prime. Okay, so let's calculate that. The transition matrix from B to B prime, right? So transition matrix from B to B prime. Well, you express the B's in terms of the B primes, right? So 1 is of course 1 of that thing, 0 of the second, and 0 on the third. Right? X is okay. X is 0 the first time, plus 1/2 of the second time, plus 0 of the last guy. And then x squared is going to be a quarter of the last guy plus half of the first guy. So 1/2 of the first guy plus 0 of the second guy plus a quarter of the last guy. Right. Right. So going from B to B prime, S of B prime is going to be the matrix 1, 0, 0, 0, 1/2, 0, 1/2, 0, 1/4. Okay, and then so that's the one going from here to here, and then the inverse matrix is going to be the inverse matrix of that guy. So B S B B prime inverse is just going to be the inverse of that. This thing's inverse. But we could also calculate it. We could also calculate it as the transition matrix from B prime back to B, right? So that is, you'd say, okay, well, let's take B prime and express them in terms of the B vectors, right? And then take transpose the matrix of coefficients, right? So you'd say we've got 1, 2x, and 4x squared minus 2. Well, that's going to be 1 of this guy, 0 of this guy, 0 of this guy. It's going to be 0, 2, 0. It's going to be -2, 0, 4. Right? We transpose that, we get 1, 0, 0, 0, 2, 0, -2, 0, 4. So that's kind of a cute way of inverting this thing. Okay. So then you say, okay. So now let's check. Let's check that if we take the AB matrix, and then hit it with this guy first, sorry, precompose it with this guy, and then hit it with the inverse matrix on the other side, then we get then we get the other guy 0, 2, 0, 0, 0, 4, 0, 0, 0. Okay, I'm not going to do it. I'm not going to do it. But in any case, if you work it out, lo and behold, it turns out that this matrix is indeed a conjugate of this matrix, and vice versa. Okay, so that's the this is what goes on in the theorem, right? So again, what's it saying? It's saying that whenever you have a linear transformation, linear operator, you have one basis and you have another basis, then the matrix representations with respect to those bases are actually conjugates of each other. Conjugates by the transition matrix, by the appropriate transition matrices. Okay. 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 So Why is that true? Right? Why is it true that, let's write it this way, ABB is the same thing as SBB prime followed by A B prime B prime followed by S inverse B B prime? Right? Why is that true? And we can actually see it just by looking at the commutative diagram. Okay, so here's the proof. Actually, here's the proof. If we go across like this, as we said before, because this thing is a matrix representation, going across here is the same thing as going up, across, and then down. Right? Right? You know, going this way and down is the same as going this way across. This part is an isomorphism. We can reverse it. Okay. So going this way is the same thing as going up, across, and then down. Same thing here, right? Going across here is the same thing as use green. Going across, going from here to here is the same thing as going up and then across and then down, right? Okay, so now think, since this thing is the same thing as going up, across, and down, we can say, let's go, this thing is the same thing as going up, and instead of it going across, right, remember, going across is the same thing as going up, across, and down here. So we go up here, and instead of doing this, we swap to the green line, and we go up, across, and down, and we follow it with a down. That's the same thing as ABB, right? Well, right, that's the same thing as going first through SBB prime, right? SBB prime, right, going up through SBB prime, going through A, B prime, B prime, and then going backwards through SBB prime. In other words, taking the inverse transition matrix down this way, right? And so that's the proof, right? That ABB is the same thing as SBB prime followed by AB prime B prime followed by SBB prime inverse. SBB prime inverse. Okay, so that is that's why that's true. Okay, so proof by picture. Okay. Right? ABB prime is the same thing as pi sub b inverse followed by t and then followed by pi sub b. But t is the same thing. T is the same thing as pi sub b prime followed by a b b prime followed by pi sub b prime. Right? Pi sub b prime inverse. Right? But this thing here, pi sub b inverse followed by pi sub b prime, that is S b b prime right? And this guy, pi sub b, pi sub b followed by pi sub b, no, sorry, pi sub b prime inverse followed by pi sub b is the same thing as s sub b prime inverse. Right? That's this. And so we get that. So we get that ABB is what we wanted. Okay, so pretty cool, right? All matrix representations of the same linear operator are going to be conjugates of each other. Okay. Okay, let me introduce the terminology. So, what does similar mean? It's what I was calling being conjugates earlier. So, is a definition. If you have A and B that are n by n matrices, and you have another n by n matrix that's invertible. So if there exists an invertible matrix such that B is equal to S inverse AS, then we say A is similar to B. A is similar to B. Okay. But notice that being similar is a two-way relation. It's a reflexive relation, right? Because if A is similar to B, well then, S inverse B equals, S inverse B, S inverse is A, right? And so B is similar to A, right? So being, if A is similar to B, then B is similar to A. Remark. It's also true that the relationship is reflexive. The relationship is also The relationship is symmetric. Sorry, right? It's symmetric. A is similar to B is B similar to A. Sorry, I said it wrong. It's also reflexive because every matrix is similar. Every square matrix is similar to itself. And you also have the relation is also transitive, right? If A is similar to B and B is similar to C, then A is similar to C. So being similar is an equivalence relation. An equivalence relation. Remember I said earlier that love is not an equivalence relation. Similarity is an equivalence relation. Okay. And so what the theorem says, what the theorem was saying, that it says that all matrix representations of the same linear operator are in the same equivalence class. Right? In other words, they're all similar to each other. Okay. All the matrix representations are going to be similar to each other. And it's also true that if you have matrices that are similar to each other, then they are representations of the same linear operator. You can also show a converse to that. So, basically what it is that every linear operator is associated with an equivalence class of matrices. And the game that we're going to play not in the next chapter, but in the chapter after that, is how do you find the best member of that equivalence class, right? You'd like to deal with the matrix representation that is the most simple, right? That is the simplest. So how do you find a good representative? And that will be the game of eigenvectors and eigenvalues. But we'll have to put that off until chapter 6. Okay, that's it. That's it. Sorry, I had to re-record it.